Come on, my dears, let us proceed further in chapter number 4. Today we are going to understand about one optical phenomenon called interference. After this, in the same chapter, we will study about two more optical phenomena, diffraction and polarization. Let me tell you one thing, in producing all these optical phenomena, there is no role played by oscillations of magnetic field, because there is no role of magnetic field while producing any optical phenomenon. What we will do, we will not consider the oscillation of magnetic field in our discussion of optical phenomena, but we will concentrate only on the oscillations of electric field. And oscillations of electric field is shown by a typical vector which is called electric intensity vector. Electric intensity vector. Okay. So we will talk about oscillations of electric intensity vector. Got it? Fine. First of all, let us see what is called an interference. What do you mean by an interference? Whenever two or more than two waves superpose at any one particle of medium simultaneously, we find that that particle starts oscillating under the resultant effect of all the superposing waves. This very phenomenon, this very effect is known as an interference in a wide sense. Physical effect arising due to superposition of two or more than two waves is called an interference in a wide sense. I repeat, physical effect arising due to superposition of two or more than two waves is called an interference in a wide sense. Okay, fine. Now, let us recall the equation, wave equation, which you had studied in second semester in 11th standard. Recall that wave equation, it was y equals to a sine omega t minus kx. At that time, this initial phase phi was 0. But if initial phase is not 0, then we have to consider that phase also. So in all, that wave equation will become y equals to a sine omega t plus phi minus kx. Fine. Now, similar equation today we will write for oscillations of electric intensity vector. See the change in the symbol. Instead of y, now you must write vector small e. Instead of capital A, now you must write vector capital E, sine as it is, omega t plus phi as it is, k as it is, but normally distance is shown in 3 dimensions by symbol small r. Okay. Just give me identification of each quantity here. What is small e? Displacement of electric intensity vector at time t. Okay. What is vector capital E? It is amplitude of electric intensity vector. Amplitude of electric intensity vector. What is omega? It is angular frequency of given wave. Here we are going to consider light wave. So it is angular frequency of light wave. T is the given time. Phi is initial phase of electric intensity vector. What about small k? It is wave vector. K equals to 2 pi upon lambda, where lambda is the wavelength. K is wave vector of given wave. And what about r? Distance of considered point on the propagation of wave, on the direction of propagation of wave, distance of considered point from source of wave. Source of wave. In short, it is distance between source and, so you can say, the point which you have considered. Okay, it is called point of observation. Point of observation. This r is the distance of point of observation from source of wave. Okay, fine. Now, consider two point-like sources. Consider two point-like sources of light waves, say S1 and S2. They emit light waves. Fine. See, this is the first wave emitted from first source, and say this is the second wave emitted from second source. Suppose these two waves superpose at this very point, say point P. At time t, when they superpose, what are the displacements of electric intensity vectors in both the waves That is what we want to write using this wave equation. Come on. Instead of vector E, I am putting vector small e1. Instead of vector capital E, here I am writing vector capital E1. Sine, instead of omega, I am writing omega 1, t as it is. Instead of phi, I am writing phi 1, minus, instead of k, I am writing k1. Instead of r, I am writing r1. Correct? Fine. Just give me identification of each quantity. This is displacement of first electric intensity vector. This is amplitude of first electric intensity vector. This is angular frequency of first wave. Given time, this is initial phase of first electric intensity vector. This is wave vector of first wave, and this is distance of considered point on the direction of propagation of first wave from the source of first wave. Correct? Fine. Now, with this sine function, the bracketed part indicates some sort of angle, and that angle I am going to show by symbol delta 1. It is also called phase of first wave. Phase of first wave. Fine. Delta 1 is this much, omega 1 into t plus phi 1 minus k1 r1. Delta 1 is omega 1 into t plus phi 1 minus k1 r1. Tell me, similarly, what would you write for displacement of second electric intensity vector? Come on, instead of vector small e1, we should write vector small e2. Instead of vector capital E1, I should write vector capital E2. Sine as it is, instead of omega 1, I should write omega 2. T as it is, instead of phi 1, I should write phi 2. Minus as it is, instead of k1, I should write k2. Instead of r1, I should write r2. Come on, give me identification of each quantity. What is vector small e2? It is displacement of second electric intensity vector. This vector capital E2 means amplitude of second electric intensity vector. What is omega 2? Angular frequency of second wave. T is considered time. Phi 2 is initial phase of second electric intensity vector. K2 is wave vector of second wave, and R2 is distance of point of observation on the direction of propagation of second wave from the source of second wave. Correct? Fine. Now this bracketed part gives me some sort of angle, which I am going to show by symbol delta 2, which gives you phase of second wave, which is delta 2, and it is omega 2t plus phi 2 minus k2 r2. And now tell me, if we want to have phase difference, between the superposing waves, let it be this way, delta 2 minus delta 1. So I am just subtracting phase of first wave from the phase of second wave. If delta is delta 2 minus delta 1, then tell me, delta 2 minus delta 1 means this minus this. So it is this minus this. Come on, omega 2t minus omega 1 into t, take t common, inside the bracket omega 2 minus omega 1, inside the bracket omega 2 minus omega 1. Then this minus this, so it is now phi 2 minus phi 1. And now this minus minus plus, so k1 r1 minus k2 r2, k1 r1 minus k2 r2, correct? So this gives you expression of phase difference between superposing waves. Fine. Now, when two light waves superpose at point P, if we want resultant displacement of electric intensity vector, and if we want amplitude of resultant wave, how can we find it? Using phasor diagram. I am going to show you. Look here. In this phasor diagram, come on, vector OA represents first phasor, which represents oscillations of first electric intensity vector. Second phasor, vector AB, represents oscillations of second electric intensity vector. And come on, resultant phasor, that is vector OB, represents resultant oscillation of electric intensity vector. I am going to show one by one. Look, this first phasor, that is vector OA, has length equal to amplitude of first electric intensity vector, that is vector capital E1, and it makes angle delta 1 with x-axis, which is nothing but phase of first wave, and component of E1 opposite to delta 1, which is this much or this much, will give you E1 sin delta 1. Component of E1 opposite to delta 1 will be E1 sin delta 1, and it is going to give you vector small e1. So come on, this much is vector small e1. Component of E1 opposite to delta 1, this much or this much. It is vector small e1, that is displacement of first electric intensity vector. Fine. Now this is second phasor, that is vector AB, and its length is going to give you amplitude of second electric intensity vector, which is vector capital E2. Fine. It makes angle delta 2 with x-axis, which is nothing but phase of second wave, and its component, come on, along y-axis is from C to D, and it is vector small e2. Correct? The way this much is small vector e1, this much is vector small e2. And don't you know, according to principle of superposition, resultant displacement will be equal to vector addition of individual displacements. So vector E equals to vector E1 plus vector E2. Vector E equals to vector E1 plus vector E2. So this vector plus this vector will make this vector, vector OD, which is nothing but resultant displacement, vector small e. Got it? Fine. Now tell me, phasor plus phasor will give you resultant phasor, and for this resultant phasor, its length is vector capital E. Now tell me, this is the direction of first phasor, this is direction of second phasor, then this much angle will give you phase difference. Come on, if this is delta 1, this also will be delta 1, because these two are corresponding angles. Correct? Now out of delta 2, if you subtract delta 1, the difference is this much, which is delta 2 minus delta 1, and delta 2 minus delta 1 is nothing but delta, which gives you phase difference between superposing waves. Now tell me, if you have got two vectors, vector capital E1 and vector capital E2, and when you add them, then vector addition is vector E, and if angle between these two vectors is delta, then how would you write magnitude of this vector? Remembered from semester 1, vector capital R, resultant vector, it was equal to vector A plus vector B. What was the angle between vector A and vector B? It was theta. At that time, magnitude of resultant vector you had written capital R equals to under root of A square plus B square plus 2AB cos theta. Similarly, here we can write E equals to under root of, come on everybody, E1 square plus E2 square plus 2 E1 E2 cos delta. Because right now the angle between these two vectors, it is not theta but it is delta. So instead of theta I am writing delta, instead of A I am writing E1, instead of B I am writing E2, instead of A E1, instead of B E2, and instead of capital R I am writing capital E. I repeat, R equals to, from 11th standard, R equals to under root of A square plus B square plus 2AB cos theta, and here E equals to under root of E1 square plus E2 square plus 2 E1 E2 cos delta. Correct? Fine. Now tell me, this is the amplitude of resultant electric intensity vector, or you can say it is amplitude of resultant oscillation, or sometimes we call it amplitude of resultant wave. Fine. And now we want expression of intensity of resultant wave at point of superposition. Come on, take squares on both the sides. When you take squares on both the sides, here it will be E square, and when you take square, square root will vanish, giving you E1 square plus E2 square plus 2 E1 E2 cos delta. Simply take square on both the sides, that's all. And now multiply by k on both the sides. In each term you just multiply by capital K. Multiply here, so it is k into E square, multiply here k into E1 square, multiply here k into E2 square. Come on, 2 as it is, instead of k, now I just split it under root k into under root k, under root k into under root k. So under root k into E1, under root k into E2 cos delta. Naturally, under root k into under root k will be under root of k square, which is again k only. Fine. Now remember one result. Intensity of light is directly proportional to square of amplitude. Not only for light wave, for any type of wave, resultant intensity. Here I am talking about average intensity. Average intensity is always directly proportional to square of amplitude. Square of amplitude. See, normally we speak intensity, but actually we mean to say average of intensity values over one periodic time, which is called average intensity. But whenever we speak intensity, you must understand it is not simply intensity, it is average intensity. In short, I am not talking about instantaneous intensity. I am talking about average intensity. If I write it by symbol I, then practically we find that intensity of wave is directly proportional to square of its amplitude. Now remove sign of proportionality, put proportionality constant capital K. So I equals to K into E square, correct? Now for first wave, instead of I, you should write I1, instead of E, you should write E1. For second wave, instead of I, you should write I2, instead of E, you should write E2. And now take square root here. So when you take square root here, it is under root of I1, take square root here, under root of K, take square root here, it is E1, take square root here, under root of I2, take square root here, under root of K, and when you take square root here, it will be E2. Now place all these values here in this equation. Come on. Wherever it is k into E square, I can write capital I. In place of this, I can write capital I. In place of k E1 square, I can write I1. In place of k E1 square, I can write I1. In place of k E2 square, I can write I2. In place of k E2 square, I can write I2. Come on, 2 as it is. Instead of under root of k into E1, I can write under root of I1. Instead of under root k into E1, I can write under root of I1. Instead of under root k into E2, I can write under root of I2. Instead of under root k into E2, I can write under root of I2. And mind well now, take care. Simply don't write cos delta, you please write average. Because these are not simply intensities, I told you, these are average values. Because all these values are average values, here also I must take average value. That's why I am putting symbol of average. Don't forget, okay? Fine. Now in this equation, on right hand side, this third term in which there is a delta, and you know delta formula is this, from which you can make out that this depends on time. Because delta depends on time, this term will also depend on time. Such a time dependent term is known by specific name. It is called an interference term. An interference term. So now onwards, treat this term as an interference term. That's what I have written here. Interference term is this term 2 into under root of I1 into I2 into average of cos delta. This term is called an interference term. Fine. Tell me, what is delta formula? Same formula written here. Same formula. No change. Okay. Same formula written here. Now what is this delta? Delta is the phase difference between two superposing waves. Correct? Now for value of delta, you may have only two choice. Either value of delta, which is phase difference, may change with time, and second choice may not change with time. Depending upon these two possibilities, we are going to get different intensity of resultant wave. Let us find them one by one. So we consider two possibilities one by one. First, if value of delta changes with time, then what will happen? And if value of delta does not change with time, then what will happen? Let us see one by one. Look, first possibility. There are two possibilities. Come on, first possibility is phase difference changes with time. If phase difference changes with time, at that time remember, the angular frequencies of two given sources are not equal. Not equal. See, for two angular frequencies, you can have two choice. Either they are equal, or they are not equal. Come on, either they are equal or they are not equal. And when omega 1 is not equal to omega 2, this term will not be 0 because omega 1 is not equal to omega 2. When this term is not 0, meaning thereby value of delta will depend on time, So as time will change, delta will change, that is phase difference will change with time. Okay, fine. Whenever phase difference changes with time between two sources, such two sources are given specific name. They are called non-coherent sources. What are they called? Non-coherent sources. If phase difference between two given sources change with time, they are called non-coherent sources. And for such non-coherent sources, what would be the value of interference term? Let us find out. In this interference term, you are finding average of cos delta. So let us find out this value first of all. Come on, average of cos delta. If we take average of this value over one periodic time, then you should find it out this way. Integration from 0 to capital T cos delta dt divided by capital T. You know how to find out average. Over one periodic time, what you should do? You should add, that is, you should take integration of all instantaneous values of cos delta at each instant of time in the interval from 0 to capital T, and then that summation should be divided by the same time interval, and then you will get average, correct? And you know, for sine or cosine, its average value is 0 over one periodic time. Got it? Fine. So when average of cos delta is 0, put it here. Put it here. When this term is 0, this interference term will be 0. And this interference term is 0, I will be simply equal to I1 plus I2. I equals to I1 plus I2. Again I repeat, this is average value of resultant intensity. Average value of resultant intensity, which is summation of average values of intensity of two given sources. Okay, fine. This is all I have talked about. Come on, non-coherent sources. Okay. Now suppose you take omega 1 equal to omega 2. If you take omega 1 equal to omega 2, then what will happen? If you take omega 1 equal to omega 2, this part would be 0. 0 into t will be 0. So delta value will be this much. And same formula written here, delta equals to phi 2 minus phi 1 plus k1 r1 minus k2 r2. Now in this term, there is no time. There is no time. So now this phase difference has become time independent. Time independent. Time independent means what? Let the time change, delta value will not change. When delta will not change with time, such sources are called coherent sources. What are they called? Coherent sources. If a phase difference between two given sources does not change with time, remain invariant with respect to time, then such two sources are called coherent sources. Okay. In case of coherent sources, what is the resultant intensity? Let us find out. Come on, here you have taken omega 1 equals to omega 2, and then in this case k1 will be equal to k2. Why? Recall the formula of wave velocity. Formula of wave velocity was v equals to omega upon k. V equals to omega upon k. For isotropic medium, the direction of, for isotropic medium, velocity of wave in all the directions is same. Because wave velocity is same for both the waves, because omega angular frequency is same for both the waves, then wave vector for both the waves must be same. So k1 must be equal to k2. When these two are equal, we can just give them same symbol, let it be small k. And then moreover, while getting emitted, the initial phases of two waves, suppose we take same. If initial phases are same, then just put all the values here, find out delta. Come on, these two are same, so this part is 0. Instead of k1 and k2, I am going to put k. So k into r1 minus k into r2. Take k common, inside the bracket r1 minus r2. Now suppose intensities of two given sources I am taking same. If intensities are same, let them be shown by symbol I dash. Just put all these values here. Come on, I equals to I1 plus I2, but I1 is also I dash, I2 is also I dash. So I dash plus I dash, I dash plus I dash, plus 2 into under root of, instead of I1 I should write I dash, into under root of, instead of I2 I should write I dash, and instead of average of cos delta, now we should write only cos delta, because now delta does not depend on time, When delta does not depend on time, cos delta will not depend on time. So when any value is keeping constant with time, you should not go for average value. You can write without average. Okay, cos delta. Fine. Now I dash plus I dash, what is it? 2 I dash plus 2 under root I dash into under root I dash. It will be under root of I dash square. Under root of I dash square is only I dash, cos delta. Now 2 I dash, if I take common, inside the bracket 1 plus cos delta, correct? Just multiply by 2, divide by 2. Multiply by 2, divide by 2. So it is now 4 I dash and here it is divided by 2. And now, don't you know cos square theta formula? Cos square theta formula is what? 1 plus cos 2 theta by 2. 1 plus cos 2 theta by 2. So now take this as theta. So what is cos square theta? 1 plus cos 2 theta means double than this. Double than this will be only delta by 2. In short, there is a formula in trigonometry, 1 plus cos delta by 2. It is nothing but cos square delta by 2, correct? And this 4 into I dash is going to give me maximum intensity of resultant wave. Because this is maximum intensity, I just show it by different symbol. Let it be capital I0. So where capital I0 is replaced for 4 into I dash, which is going to give you maximum resultant intensity. Fine. Now instead of this, just put I0 and this is nothing but cos square delta by 2. So this is the final formula for intensity of light at the point of superposition. I equals to I0 cos square delta by 2. But what is delta formula? Delta formula is K into R1 minus R2. Delta formula is K into R1 minus R2. Correct? Fine. Now in practice we find two main types of interference. One is called constructive interference, another is destructive interference. In textbook they have not drawn any figure, you may not understand, better you concentrate here. First of all we go for constructive interference. What do you mean by constructive interference? Look, consider two waves having same frequency, same wavelength, same amplitude, which are superposing on each other as per the diagram. Look, crest on crest and trough on trough. First wave I have shown with the blue color, second wave I have shown with the yellow color, and you can see how are they superposing. Come on, crest on crest, trough on trough, correct? And when two waves superpose in this manner, it so happens that this resultant wave has this amplitude maximum. If this amplitude is maximum, whenever you know intensity of light is directly proportional to square of its amplitude. If amplitude is maximum, naturally intensity of light wave will also be maximum. And whenever intensity of resonant wave is maximum, we say two superposing waves are interfering each other constructively. How? Constructively. That's why the name of interference is constructive interference. When we get maximum intensity of resonant wave at a point of superposition, we say the type of interference between superposing waves is constructive. Fine. Now what are the conditions for obtaining constructive interference? Let us obtain first in terms of phase difference, later on in terms of path difference. Come on, phase difference, delta, I just assume to be 2n pi radian. If it is 2n pi radian, then what would be the intensity? Let me find. Come on, values of n are, come on, the value of n is variable, it ranges, it changes this way, n equals to 0, 1, 2, 3, dash, dash, dash. Come on, put n equal to 0 here first. And before that, recall the formula of intensity. I equals to I0 cos square delta by 2. I equals to I0 cos square delta by 2. I equals to I0 cos square delta by 2. What is delta? Delta is 2n pi. Delta is 2n pi upon 2. 2 will cancel, giving you cos square n pi. Cos square n pi. N value is changing this way. 0, 1, 2, 3, dash, dash, dash. Put here n equal to 0. Cos 0 is 1. 1 square is 1. 1 into I0 is I0. I equals to I0. What is I0? Maximum intensity. Fine. Then put n equal to 1. 1 into pi, pi. Cos pi is minus 1. Square will be plus 1. 1 into I0 is I0. Put n value 2. Then cos 2 pi is 1. 1 square is 1. 1 into I0, that is I0. Correct? In short, whatever the value of n may be from this range, then every time value of this term comes out to be 1. 1 into I0 is I0, which is maximum. And whenever intensity of resonant wave is maximum at the point of superposition, we say type of interference is constructive. That is why this is called condition of constructive interference in terms of phase difference. Now let us obtain in terms of path difference. Same formula of delta I have written here. Delta equals to 2n pi. But what is the formula of delta? Formula of delta is k into R1 minus R2. Delta is, come on, k into R1 minus R2. That equals to 2n pi. What is k wave vector? 2 pi upon lambda into R1 minus R2 equals to 2n pi. Pi will cancel. Find out R1 minus R2. Take this lambda here. 2 also will get cancelled. So R1 minus R2 will be, come on, n lambda. R1 minus R2 equals to n lambda. Path minus path will give you path difference. And that path difference has come out to be n lambda. Okay, where values of n are 0, 1, 2, 3 dash dash dash. Got it? So what are the conditions for obtaining constructive interference? These two are the conditions. This is the condition in terms of phase difference, which is delta equals to 2n pi radian, where values of n are 0, 1, 2, 3 dash dash dash. And condition in terms of path difference is this: R1 minus R2 equals to n lambda, where values of n are 0, 1, 2, 3 dash dash dash. Got it? Now let us see what is called destructive interference. Suppose two waves having same frequency, same wavelength and same amplitude superpose on each other as per this diagram. Look, crest of first wave superposes on the trough of second wave. Trough of first wave superposes on the crest of second wave. If this is the case, then resultant amplitude is 0. At all these points, resultant amplitude is 0. When amplitude of resonant wave is 0, naturally intensity of resonant wave will also be 0, because intensity is directly proportional square of amplitude. When amplitude is 0, intensity has to be 0. So intensity is 0. And whenever resultant intensity is 0, we say the type of interference is destructive. So these two waves at present are interfering each other destructively and producing resultant intensity which is 0. And when intensity of light wave is 0 at any point, that point will be seen dark. That point will be seen dark. Okay. If intensity is maximum, point will be bright. If intensity is 0, point will be appearing dark. What are the conditions for obtaining destructive interference? First, let us obtain in terms of phase difference, then in terms of path difference. Phase difference here I assume to be 2n minus 1 into pi radian, where values of n are 1, 2, 3 dash dash dash. Come on, I equals to I0 cos square delta by 2. I equals to I0 cos square delta by 2. What is delta? 2n minus 1 into pi upon 2. Just put value of n equal to 1 here. 2 into 1, 2. 2 minus 1 is 1. 1 into pi is pi. Pi by 2. Cos pi by 2 is 0. Its square is 0. 0 into I 0, 0. So I equals to 0. Put n equal to 2 into 2, 4 minus 1, 3. Cos of 3 pi by 2 is 0. 0 square will be 0. 0 into I 0 will be 0. I equal to 0. I mean to say, you may put any value of n out of this range. Every time this value comes out to be 0, 0 into this will be 0. And when intensity of resonant wave is 0 at the point of superposition, at that very point, which type of interference will take place? Destructive, because intensity is 0. Correct? So this becomes now condition for obtaining destructive interference in terms of phase difference. Now let us obtain in terms of path difference. Come on, delta formula. Delta formula is this: delta equals to k into R1 minus R2. Right now delta is 2n minus 1 into pi. Delta is 2n minus 1 into pi. Delta formula is k into R1 minus R2. Right hand side as it is. But what is wave vector k? K equals to 2 pi upon lambda. This part as it is, this also as it is. Pi will cancel. Find out R1 minus R2. Take this lambda up and bring this 2 down. So 2n minus 1 into lambda upon 2. Correct? Path minus path will give you path difference. So now this becomes the condition for obtaining destructive interference in terms of path difference. Correct? These two are conditions for destructive interference, where values of n are changing 1, 2, 3 dash dash dash. These two are the conditions for constructive interference in which value of n changes like 0, 1, 2, 3 dash dash dash. Okay, fine. Come on, my dears. Now let us consider two point-like coherent sources. You must have remembered the definition of coherent sources. Sources which have constant phase difference at all the times are called coherent sources. Sources having constant phase difference at all the times between them are called coherent sources. Fine. Now consider two point-like coherent sources. Come on, they are S1 and S2. They are point-like coherent sources. Distance between them I am taking as small d. Fine. Now, in front of these two point-like sources, I just place here, come on, one screen. Fine. So this is the screen which is placed at perpendicular distance capital D from these sources. Mind well, this small d distance is very small. It is of the order of 10th part of a millimeter, and this capital D distance in comparison is very large, of the order of meter. This is of the order of 10th part of a millimeter, and this is of the order of a meter. Okay, this is very small, this is very large. Actually, these 2 point-like coherent sources you are supposed to consider almost adjacent, that much close they are. Okay. Here, just to have clarity in the figure, I have shown them far separated, but actually they are very close to each other. Okay, fine. Now, the light rays emitted from these two sources are made incident, say, at point P. So, at point P, there is a superposition of two light waves, and you know, whenever there is a superposition of two or more than two waves, we will have a phenomenon called interference. So, superposing waves will interfere, and depending upon type of interference, we will have some sort of some value of intensity, If type of interference is constructive, you know, we will get maximum intensity. This point will appear as bright point. If type of interference is destructive, then because of zero intensity, this point will appear as dark point. Okay, fine. Now, this distance of point P from first source I am taking R1, distance of point P from second source I am taking as R2. Fine. And here we have to find out the expression of path difference, that is greater path minus smaller path. Come on, path difference I am taking R2 minus R1. Okay. Let us find out formula for R2 minus R1. Distance of point P from this center point on the screen is Cp, and the Cp distance I have shown by symbol x. Fine. Now just join O and P. In the whole figure, remember, wherever I have shown arrows, they are light rays. If I have not shown the arrows, means they are not light rays, they are simply line segments. Now just draw one perpendicular from S1 onto this line segment S2P. Foot of perpendicular is capital M, and now find out this much distance. That will give you path difference between these two light rays, because this is greater path, this is smaller path. Now this path minus this path if you take, then this much is the path difference between them. It is S2M. Okay, wait. Now here these three you may not find parallel in this figure. These three you may not find parallel, but actually near to these sources, these three are nearly parallel. They are like this. You can see this one line segment, another, and third one. These two are light rays, and this is the line segment OP, correct? S1P, OP, and S2P. They are nearly parallel in the region near to the sources. You know why? Because actually speaking, this small d is very small, capital D is very large. So situation is this, that these three are nearly parallel. And in that case, if you draw a perpendicular on this line, it would be perpendicular on this line also. So here also I have shown right angle, here also I have shown right angle, and in that case, if this angle is theta, these also will be theta, because you know angle between two given line segments and angle between their perpendiculars are always equal. Angle between these two line segments, it is theta. Angle between their perpendiculars also must be theta. Perpendicular to this is this, and perpendicular to this is this. So these two angles are equal. These two angles are equal. Correct? Fine. Now this angle I have shown here theta. This angle is also theta. Fine. Now just find out sin theta. In this right angle triangle, you just find out sin theta. Opposite to theta, that is S2m, divided by hypotenuse, that is opposite to right angle, which is small d. Fine. In this right angle triangle OCP, now find out tan theta. Tan theta means opposite to theta divided by adjacent to theta. Opposite to theta is x, and adjacent to theta is OC, or you can say capital D. Opposite upon adjacent. Okay. Now I want path difference between the paths travelled by two light rays in order to reach point P after getting emitted from these two sources. Fine. That path difference is greater path minus smaller path. Greater path is this, which is R2. Smaller path is this is R1. Greater path length is R2, smaller path length is R1. What is R2? From the figure, R2 is S2P, S2P, minus R1 is S1P, S1P. Fine. What is S2P? S2P is nothing but S2M plus MP, S2M plus MP, minus S1P. But because MP and S1P are equal, MP and S1P are equal, because these two are equal, they will cancel and giving you S2M. But what is S2M from here? Transfer this. S2M will be d sin theta. S2M is d sin theta. And here, actually speaking, this theta value is very, very small. You may not find very small in the figure, because in the figure this small d is shown very large. When you take small d very small and capital D very large, really this theta is very, very small. Whenever theta is very small, sin theta is nearly equal to tan theta. So instead of sin theta, I am just writing tan theta. Come on, d as it is. What is tan theta value? Right now it is x upon capital D. X upon capital D. Tan theta is x upon capital D. Come on, write it properly. X into small d upon capital D. X into small d upon capital D. This gives you necessary expression for finding path difference. Okay. Remember this formula. Later on we are going to use it. Now, for coherent sources, what can be intensity of light at the point of superposition? That formula we have derived just now. Come on. I equals to I0 cos square delta by 2. Remembered formula? I equals to I0 cos square delta by 2. Remembered? But that delta was how much? Delta was K into R2 minus R1. Correct? Whether you write here R1 minus R2 or you write R2 minus R1, it makes no difference, because cos of minus theta is as good as cos theta. So don't bother for that. And instead of I am writing IP, because at present I am finding intensity of light at point P. That's why I am putting IP. Okay. What is I0? Maximum intensity. I0 is maximum intensity. Fine. Now IP as it is, I0 as it is, cos square as it is, K upon 2 also as it is. Now R2 minus R1 formula. R2 minus R1 formula, you may write d tan theta. D tan theta. So this R2 minus R1 I am replacing by d tan theta. Fine. Now I0 as it is, cos square as it is, K upon 2 as it is. Correct? Instead of R2 minus R1, you may write, instead of R2 minus R1, you may write xd upon d, xd upon d. So instead of R2 minus R1, you may write x into small d upon capital D. This is formula of intensity of light in terms of angle theta. This is the formula in terms of distance x. Okay, fine. Now, here I0 is constant, K is constant, 2 is constant, capital D is constant, small d is constant. For a given point, value of x is also constant. For a given point, x is constant. I mean to say whole right hand side is constant, so left hand side IP also will be constant. And if at a given point intensity remains constant with time, it does not change with time, then the type of interference is called stationary interference. What is it called? Stationary interference. In case of given interference, if intensity of light at every point on the screen does not change with time, then that interference is called stationary interference. I repeat, an interference in which intensity of light at every point does not change with time is called stationary interference. One thing sure, that at different points intensity might be different. At different points intensities might be different. But at a given point, if intensity does not change with time, then that sort of interference is called stationary interference. Correct? In that case, on this screen, correct, certain points you will get bright points because of maximum intensity, certain points you will get as dark points because of zero intensity, and certain points having intensity more than 0, less than maximum. More than 0, less than maximum intensity. Okay? So you can say they are partially bright, partially dark, like that. So you will get some definite pattern on the screen, and that pattern will not change with time. Such an interference observed on the screen is called stationary interference. Now we are interested in finding out what is the most important condition for obtaining stationary interference. Very simple. You know this equation, IP equals to I0 cos square delta by 2. Now tell me, I0 is constant and you want IP to remain constant, then it is implied that delta must be constant. Delta must be constant. Then if delta is constant, then this right hand side will be constant, then this IP also will remain constant. It will not change with time. But you know, when delta is constant, two sources having constant phase difference between them at all the times are called coherent sources. So what is the most important condition for obtaining stationary interference? That important condition is that the sources must be coherent. Sources must be coherent. That gives you most important condition for obtaining stationary interference. Correct? Fine. Now, let us talk about non-coherent sources. Non-coherent sources. You consider a pair of electric bulbs kept in some room. If you keep here a pair of two electric bulbs, and if you switch them on, then naturally they will just emit light waves, and those light waves are made incident at every point on the wall in that room. Now what do we find? That the pattern observed on all the walls, that pattern remains as it is. Correct? So you will be misguided that when pattern remains as it is, it might be stationary interference. That is what you may think. Actually, it is not stationary interference, because see, when you are passing current through the filaments of these two bulbs, actually you are spending electrical energy, and because of energy given to the electrons in the filament, they make transitions from lower to higher energy states. But in the higher energy states, they are rather excited, they are not stable, and then after some time they will just make transitions in the lower energy state. At that time they will emit light waves. But because of random transitions, the light waves are also emitted randomly, and because light waves are emitted randomly, they have phase difference between them constantly changing with time. If delta is changing constantly, then intensity of light at a given point will go on changing constantly with time. And if intensity of light at a given point changes with time, then such an interference is not stationary interference, because here delta is changing, and when delta is not constant, the sources are called non-coherent sources. So no doubt this pair of bulbs will be common sources of light, but which sort of sources? They are non-coherent, because delta is continuously changing, and because you have non-current sources, you cannot expect stationary interference. Correct? In fact, you know what happens? At every point on the wall in that case, the intensity of light goes on changing rapidly, very quickly. It might be changing thousands of times in 1 second. And because of law of persistence of vision, you know, if any change appears to take place more than 16 times in 1 second before human eye, then human eye cannot detect between two consecutive changes. That is why any observer will find average intensity of light at all the points on the screen or on the wall, and because he is finding average intensity and the pattern is remaining same, then he might be misguided that this is stationary interference. Actually, it is not stationary interference. At every point, intensity goes on changing with time because of pair of non-coherent sources, correct? Same way, in the year 1665, Mr. Grimaldi was also misguided. Mr. Grimaldi had used sunlight and some holes, and through the holes he was passing the sunlight, but when through the two holes, if you are passing sunlight, no doubt those two holes will become sources of light, but sunlight is also having non-coherent waves in it, and because of superposition of non-coherent waves having constantly changing phase difference between them, naturally you will not have stationary interference. So, Mr. Grimaldi actually did not get stationary interference, correct? He got average values of intensity on the screen, okay? Fine. Now, there are two methods you can obtain coherent sources. Which two methods? Very simple. First is division of wavefront, for which quite thin or narrow source is required. Division of wavefront in which quite narrow or thin source is required. Another is division of amplitude, where you require extended source, the source which is spread, okay, over a large region, which is called extended source. Here we require very thin or narrow source. Here we require, for the division of amplitude, we require source which is called extended source, okay. In our syllabus, we have to study this by division of wavefront. How can you get coherent sources? I am showing you. Before that, let us distribute intensity of light at various points on the screen using this formula. Using this formula, you can plot a graph of intensity versus angle theta. Intensity I am taking on y-axis, angle theta I am taking on x-axis. Here I am showing positive values of theta, here I am showing negative values of theta. Fine. Now, from this equation, if you plot a graph of I versus theta, that graph is like this. Repeated inverted parabola. Fine. Here it is maximum intensity, which is I0. And you know I0 is 4 I dash. So, if you take fourth part of this, it will be I dash, and fourth part of this much, suppose it is this much, it gives you I dash. I dash is intensity of single source, and I0 is maximum intensity, which was replaced, this I0 symbol, you know, in the earlier formula. This I0 was how much? I0 was 4 I dash. So, this I0 is 4 I dash. Fine. Now, look. There is a general formula also. I0 at present it is 4 I dash. 4 you can always write this way, 2 square, correct, into I dash. But what was 2 at that time? Number of coherent sources. If number of coherent sources is 2, then you get intensity, maximum intensity as 2 square into I dash, where I dash is intensity of single source. Now, likewise, you may have n number of coherent sources. And if the waves emitted from them having same intensity, if they are incident on a particular point, then at that point, what would be maximum intensity of light? It is given by this formula. Instead of 2, you just write number of coherent sources, that is n, each having same intensity, that is I dash. So, maximum intensity in that case, it would be n square I dash, where capital N is total number of coherent sources. Fine. Now, here, when theta values are 0, 2 pi, 4 pi, you get maximum intensity. Maximum intensity of light means what? Bright points, okay? And here for theta values pi, 3 pi, 5 pi, minus pi, minus 3 pi, minus 5 pi, you are going to have destructive interference. That's why intensity is 0, correct? When intensity is 0, those points will appear as dark points. Constructive interference, maximum intensity, bright point. Destructive interference, 0 intensity, dark point. Got it? Fine. Now, what is the distance between two consecutive bright fringes? Fringes means strips, you can say, strips. On this screen, you know, At some positions we get bright fringes, bright strips. What is the distance between two consecutive fringes? Let us find out. Suppose here I am getting particular order bright fringe, say at point PM, and its distance from central bright fringe I am taking as xm by symbol. M you must write below x. And after M, what is the next order? After M it will be M plus 1, correct? Next consecutive order would be M plus 1. So this point is P M plus 1, and distance of this M plus 1th order bright fringe from this central bright fringe I am taking as x M plus 1, correct? Now tell me, what is the distance between two consecutive bright fringes? Suppose it is x bar. Suppose it is x bar. Then from this figure, can you make out x bar? How would you find it? xm plus 1 minus xm. Yes, here it is. X bar equals to xm plus 1 minus xm. Okay, that is distance between two consecutive bright fringes. Come on, x bar equals to xm plus 1 minus xm. Bright fringe. Bright fringe means maximum intensity. Maximum intensity means construct interference. Construct interference means path difference must be equal to n lambda. Just now we have obtained the condition for obtaining construct interference. Condition was path difference should be equal to n lambda. Path difference should be equal to n lambda. But what is the expression of path difference? It is x into small d upon capital D. Come on, x into small d upon capital D. But instead of x I am putting xn. N you must write below x. Okay, fine. Now find out xn from here. It will be n lambda d upon d. N lambda d upon d. Now instead of n, just put m. N equal to, for n equal to mth order bright fringe, just put n equal to m. Here also n equal to m. And after m, what is next consecutive order? M plus 1. So instead of n, I should write m plus 1. Here also instead of n, I should write m plus 1. Correct? And now what is x bar? Come on, x bar is xm plus 1 minus xm. X bar is xm plus 1 minus xm. So it is this minus this. So it is this minus this. But when you take this minus this, lambda d upon d can be taken common. Inside the bracket m plus 1 minus m. Come on, m plus 1 minus m. M will cancel, giving you lambda d upon d. Come on, lambda d upon d. Correct? This gives you formula for finding distance between two consecutive bright fringes. And now we go for finding distance between two consecutive dark fringes. Fine. Dark fringe, zero intensity. Dark fringe means zero intensity. Zero intensity means destructive interference. Destructive interference means path difference should be equal to. Just now we have obtained the condition for obtaining destructive interference in terms of path difference. It was path difference equals to 2n minus 1 lambda by 2. Path difference equals to 2n minus 1 lambda by 2. 2n minus 1 lambda upon 2. 2n minus 1 lambda upon 2. Correct? This is the path difference, and you know the formula of path difference. Formula of path difference is x into small d upon capital D. Come on, x into small d upon capital D. Instead of x, I am putting xn. N you should write below x. Okay? This is path difference. It should be equal to 2n minus 1 lambda by 2. Then only destructive interference will take place. Then only point will appear dark. That's why I am putting here dark fringes. Okay? Fine. Find out xn from here. Capital D will go up. Small d will come down. 2n minus 1 into lambda into capital D upon 2 into small d. Now just put n equal to m. N equal to m. Put it here. N equal to m. Put it here also. N equal to m. And now after m, what is next consecutive order? It is m plus 1. So instead of n, I should write m plus 1. Instead of n, I should write m plus 1. Correct? And now tell me, just put it in bracket. Put it in bracket. Now open the bracket. 2m plus 2 minus 1. Plus 2 minus 1, that is plus 1. So it is 2m plus 1 lambda d upon 2d. Lambda d upon 2d. Correct? And now I want distance between two consecutive dark fringes. It should be xm plus 1 minus xm. Xm plus 1 minus xm. So it is this minus this. So it is this minus this. And when you take this minus this, what part you can take common? Lambda d upon 2d. Come on, lambda d upon 2d. This much part you can take common. Inside the bracket, now it is 2m plus 1 minus this. 2m plus 1 minus this. Minus 2m minus minus plus 1. 2m and 2m will cancel. 1 plus 1, 2. This 2 and this 2 will cancel. This 2 and this 2 will cancel. Giving you lambda into capital D for small d. lambda into capital D upon small d. Now match the right hand sides. Right hand sides are same, so left hand sides also must be same. X bar must be equal to x bar dash. So what we have proved? Distance between two consecutive bright fringes and distance between two consecutive dark fringes are same. Correct? Fine. Mind well, it is here capital D in the numerator, small d in the denominator. Here small d is there in the numerator, capital D is there in the denominator. Don't get confused. Okay? Fine. Now we go for very good article, Thomas Young's double slit experiment to obtain coherent sources. Thomas Young's double slit experiment to obtain coherent sources and then after stationary interference. Come on. In 1801, there was English doctor, British doctor, Mr. Thomas Young, who had devised first ever method of obtaining coherent sources in the entire world. What was that method? I am showing you. He had taken three screens, and he had kept them parallel to each other. They were A, B and C. These are three screens which are kept parallel to each other. Fine. Distance between these two screens is small and between these two the distance is quite large. Fine. Now tell me, in this screen we have one extremely thin vertical gap which normally we call slit. So this vertical gap, vertical opening is called slit, shown by symbol S. In this screen B, we have two slits, S1 and S2, which are also very thin, very close to each other. Distance between them is 10th part of a millimeter and they are equidistant from this slit S. Distance SS1 and SS2, they are equal. Distance is SS1 and SS2, they are equal because this slit is lying on the perpendicular bisector of the line segment joining these two slits perpendicularly. And because this is lying on the perpendicular bisector, distance SS1 is equal to SS2. Fine. Now in front of this slit, we just place here linear monochromatic source of light waves. Linear source though you know, correct? What about monochromatic? Monochromatic source is that which emits light waves with constant frequency or constant wavelength. Such a source is called monochromatic source. It emits it emits light waves with a particular color. For example, if you take sodium lamp, it emits light waves with precisely this much wavelength, 5896 angstrom, which is pertaining into yellow color. So sodium lamp emits yellow colored light. Fine. Now when there is a linear source, it would emit cylindrical wavefronts. So out of this source, cylindrical wavefronts are emitted, and those emitted wavefronts will just propagate. And here I have shown some small part of the cylindrical wavefront which is made incident on this slit. That small part is again cylindrical. Okay. What do you mean by wavefront being incident on the slit? Meaning is that this slit will be illuminated by yellow light. So now this slit appears yellow. Now tell me, can't you select some points on this slit? Yes, they are the points on this wavefront. And don't you know, according to Huygens principle, all the points on any wavefront behave like self-independent secondary source and they emit secondary spherical waves. Consider emission of secondary spherical waves in these two directions, from S to S1 and from S to S2. Because these two distances are equal, it will so happen that secondary spherical waves will reach here at these two slits simultaneously because distances are equal. And medium between these two is isotropic, having same velocity of propagation in both the directions. Fine. So at these two slits, secondary spherical waves will come at a time. And don't you know, the second part of Huygens principle, after infinitesimal small interval of time, a surface circumscribing to all these new secondary spherical waves gives the shape and position of new wavefront. So that new wavefront will be like this, which is made incident on both the slits at a time, and the shape is maintained. If original shape was cylindrical, the new shape is also cylindrical. Because these two slits are very close, the same wavefront is made incident on both the slits. Not only that, that too simultaneously. So both the slits are now getting illuminated at a time. And now tell me, if you select points on these two slits, they are actually points on this wavefront, and every point on a wavefront, you know, they will behave according to Huygens principle, will behave like secondary spherical source, secondary spherical, they will behave like secondary sources, and then after they will emit secondary spherical waves. So all these, both the slits, you know, they will behave like self-independent secondary sources, will emit secondary spherical waves. But because these are the points on the same wavefront, just recall the definition of wavefront. An imaginary surface passing through the particles or points having same phases of oscillation or having constant phase difference between them are called wavefront. Here, this is the wavefront, and because this is the wavefront, according to definition of wavefront, come on, an imaginary surface passing through the points or particles having same phases of oscillation is called wavefront. So if this is a wavefront, then all these points will have same phases of oscillation. And if they have same phases of oscillation, then phase difference would be 0. And this 0 phase difference will be maintained constantly. And don't you know, sources having constant phase difference between them are called coherent sources. So these two slits, not only they are secondary sources, but they will behave like coherent sources. And if you have coherent sources, then naturally they will produce stationary interference. Come on, that stationary interference is observed on the third screen, which is C. And in this screen, you will find vertically arranged, alternatively arranged bright and dark fringes that indicate stationary interference. Look, all these fringes have equal width. These are bright fringes, and between each two consecutive bright fringes, there is a dark fringe also. And distance between these two consecutive bright fringes, suppose it is x bar. Distance between two consecutive dark fringes, I am taking x bar dash. Just now we have proved that x bar equals to x bar dash. X bar equals to x bar dash. Okay. Let me repeat the last explanation. Here actually what happens, that from slit S onwards, the secondary spherical waves move in these two directions. In fact, they are moving in all the directions, but we are concentrating on these two directions, from S to S1 and S to S2. Because S1 and S2 distances are equal, it will so happen that the moment secondary spherical wave will reach at S1, same moment secondary spherical wave will reach at S2 also. I mean to say, these two slits are getting illuminated at a time. And if you just think of a surface tangential to all those secondary spherical waves, it will give you cylindrical wavefront. And now recall the definition of wavefront. An imaginary surface passing through the points or particles having same phases is called a wavefront. An imaginary surface passing through the particles oscillating with same phase is called a wavefront. So if this is a wavefront, then all these points on these two slits must have same phases of oscillation. If phases of oscillation are same, phase difference would be 0. That 0 phase difference is maintained constantly, and you know, two sources having constant phase difference between them at all the times are called coherent sources. So these two slits will behave like coherent sources. And once you have pair of coherent sources, naturally they will produce stationary interference, which is observed on the third screen in the form of alternatively arranged bright and dark fringes, in which we realize that whatever is the distance between two consecutive bright fringes, same is the distance between two consecutive dark fringes. And theoretically also we have proved x bar equals to x bar dash. Okay. Actually, history says that Mr. Thomas Young had initially not adopted this experimental setup. No, initially he had used sunlight and a very small hole, correct, which is called pinhole. He had used pinhole and sunlight. Because he had used pinhole and sunlight, you know, in sunlight there is a combination of all 7 colors. At that time he got fringes circular, because the hole is circular. He got the fringes in the shape, you know, they were circular, and only the central fringe was obtained white because of equal combination of all 7 colors. The central fringe was obtained white, and all other surrounding fringes were obtained colorful, because he had used sunlight. He had not used monochromatic source of light. Okay, and because the pinhole is having shapes like a circle, the rings will obtain circular rings instead of vertical fringes, vertical strips. He had obtained circular rings. Okay.